Hello. I've spent the last few years building ML platforms, scaling experiments, and deploying models that serve thousands of requests per second. This channel isn't about flashy tech deep dives or chasing the latest buzzword. It's about going back to fundamentals and doing things by first principles. I wanted to start with something basic. So let's talk about experimentation when building machine learning models. When we talk about experimentation, we're really talking about the cycle of trying out different modeling ideas in a structured way. It's the process of asking, what if I change this piece of the model pipeline? Will it actually improve performance? For example, maybe you wonder if normalizing your inputs differently will help. Or if adding more features, tweaking hyperparameters, or switching from one algorithm to another makes a difference. Rather than guessing, you set up an experiment, train the models, compare the metrics, and see what holds up. Why does this matter? Because building ML models is full of uncertainty. There's no single recipe that works every time. Without experimentation, it's easy to get stuck chasing hunches or overfitting to what should work. Experimentation gives us evidence. It tells us whether that new preprocessing step or parameter change is truly better, or just noise. It also helps us learn systematically. Each experiment is not just about winning or losing, it's about building intuition. Even when a change doesn't improve the model, it teaches us something about the data or the algorithm that we carry into the next iteration. So at the core, experimentation in ML matters because it's how we separate signal from noise. It's how we move from, I think this will work, to, I know this works, because I tested it. So, once you start running experiments, the real question becomes, how do you actually keep track of them? If you're just trying things randomly and relying on memory, it's almost impossible to know what worked and what didn't. You need a system. Think of each experiment as a data point. You wouldn't run a model without logging its inputs and outputs, right? The same principle applies here. For every experiment, you should capture what you changed, what stayed the same, and what results you got. This turns experimentation from trial and error into a repeatable process you can actually learn from. What should you log? At minimum, the configuration, hyperparameters, features used, model type, git commit hashes. The dataset, which split, what version, any preprocessing applied. The results, metrics, plots, model weights. And most importantly, the intent or a decision log. Why you ran the experiment in the first place. That last one matters because two experiments with the same setup might have very different goals. When you do this consistently, two things happen. First, you avoid repeating mistakes. Second, you start seeing patterns. For example, you might notice that every time you normalize inputs differently, your model becomes more stable. These insights compound over time, but only if you've tracked the journey. So the way to think about tracking experiments isn't as extra overhead. It's the actual foundation of progress. The logbook of your experiments becomes the story of how your model improved. And the more disciplined you are about it, the faster you'll move from hunches to reliable results. When it comes to tooling for experimentation, the truth is, you don't need to start with anything complex. Many teams begin with something as simple as an Excel sheet. You just log the experiment name, the model version, what data you used, and the performance metrics. It may sound basic, but that simple discipline already makes your process more repeatable and avoids the classic problem of, wait, which notebook gave us that result again? Now, this works fine when you're running a handful of experiments on your own. But let's imagine you are working with multiple teammates who are all trying different hyperparameters, maybe training models daily. Suddenly, you've got dozens of runs floating around, files scattered on laptops, and results shared in Slack. That's when tracking in spreadsheets becomes painful. you spend more time organizing results than actually experimenting. This is exactly the point where tools like MLflow or weights and biases come in. They automate the heavy lifting, capturing parameters, metrics, and even artifacts like models or plots without you manually writing them down. They also give you dashboards so you can line up runs side by side and quickly see which ideas are working and which aren't. The key benefit isn't the brand name, it's what these tools unlock. Repeatability, being able to recreate an experiment exactly. Collaboration, making it easy for your teammates to see and build on your work. Speed of iteration, because you're not wasting time digging through files or messages to compare results. Scaling experimentation isn't just about adding more GPUs or plugging in a tracking tool. The real challenge is keeping experiments organized, reproducible, and meaningful across multiple teams. Here are some things to keep in mind. Naming conventions matter. If every experiment is called Test 1 or Final _model V2 really final, you've already lost. When results are buried in poorly named runs, you end up wasting time digging through history or worse, rerunning the same experiments. Instead, create a shared naming schema. Include the project, dataset, model type, and maybe even the objective. Something like this could be meaningful. It's not glamorous, but it makes experiments searchable, comparable, and shareable across the org. Naming conventions sound small, but they're the first guardrail against chaos. Standardized repos. Every team should not be reinventing basic setup. Without consistency, you get a patchwork of scripts, configs, and logging styles that no one outside the original author can parse. The solution? A standardized Git repository template. Pre-baked configs, logging utilities, and evaluation scripts into it. Make it the starter kit for every new project. This ensures experiments look and behave the same way across teams, cutting down overhead and accelerating collaboration. Go beyond metrics. Accuracy, F1, or AUC might tell you how well a model fits your data, but they don't tell you if the model works in production. You need to track latency, memory usage, and robustness. And when GPUs are involved, hardware tracking becomes critical. Log GPU type, driver version, and utilization patterns. For multi-GPU training, watch communication overhead and node failures. Multi-GPU scaling often breaks not on speed, but on bottlenecks and silent inefficiencies. Decision logs. Numbers alone don't tell the story. What really matters is why you made a choice. Did you try approach B because model underfit? Or because it aligned better with business requirements? Keeping a lightweight decision log avoids teams repeating dead ends and builds institutional knowledge. Over time, this log becomes as valuable as the experiments themselves. It tells the narrative of your model's evolution, not just the outputs. Culture of sharing. Process and tools can take you far, but culture completes the picture. If teams hoard their experiments, you get silos where the same mistakes happen repeatedly. Create channels for sharing, weekly experiment reviews, cross-team updates, or lightweight documentation hubs. And importantly, loop in product teams early. Experiments should tie back to real-world constraints, not just leaderboard scores. A model with 99% accuracy but 2-second latency may be useless for production. By involving product, you ensure experiments move the needle where it matters. Scaling experimentation equals disciplined process plus collaborative culture. With the right guardrails, your organization doesn't just run more experiments, it learns faster, avoids repetition, and delivers results that actually matter. Alright, let's wrap this up with a quick summary. First, compare models holistically. Look beyond just model metrics. Consider a model's efficiency and how it fits into real-world constraints. A simpler model that's fast and robust might be a better choice than a slightly more accurate but slow and fragile one. Second, experiment with intent. Every experiment should have a clear hypothesis. Define what you're trying to prove before you start. Then, track with discipline. Log your experiments diligently. And finally, evaluate with context. A model that performs well on a benchmark might not be the best solution for your specific business problem. Teams that experiment well don't just build better models, they learn faster. And in machine learning, speed of learning could give you the ultimate competitive edge. Please like, share and subscribe for more such content.